All for the design of reinforced concrete structures course. In this, we will discuss about CDT 37, that is your analysis and design of rectangular beams by using working stress method of design. So in working stress method of design, the difference between limit state method of design and working stress method of design, the stress variation. So in working stress method of design, stress variation is considered as a linear. Stress variation is considered as a linear. So this is a stress variation. This is considered a singly reinforced beam. So this is your effective cover. This is effective cover, and it is a effective depth. This is your effective depth, and it is neutral axis. Neutral axis. Small n is the neutral axis depth from the top fiber to the neutral axis. Neutral axis depth is small n. The remaining portion from the neutral axis to the rebar at the tensile zone. So tensile zone, that is D minus n. D minus n. So now I am considering a coefficient, neutral axis coefficient k for the calculation of neutral axis depth n. N is equal to, I am considering k times of d, and so if you substitute n is equal to k times kd, then this length will become d minus kd. So now the maximum stress in the concrete, maximum stress in concrete sigma c, and the maximum stress in steel sigma s, let us say. So for the analysis purpose, I am considering this is sigma c. So generally we call sigma cbc, and it is called sigma st. Okay, so sigma st. Now we'll discuss about especially on working stress method doubly reinforced beam. Necessity of doubly reinforced beam. So generally doubly reinforced beam is nothing but the reinforcement is provided in tension zone as well as compression zone. Then we call the rectangular beam as doubly reinforced beam. So let us say this is your neutral axis. Neutral axis, above the neutral axis, the fibers, concrete fibers under compression, and below the neutral axis, the concrete fibers under tension. So because of this tensile forces, the crack may develop at the bottom of the beam. So to avoid the tensile cracks, tensile reinforcement, we will reinforce with the beam with steel. That is, the reinforcement will be provided at the bottom. So because of this reinforcement, the tensile cracks we can arrest the tensile cracks, right? So this is singly reinforced beam. But in case of doubly reinforced beam, we generally provide the reinforcement at the bottom fiber as well as the top fiber. So why we will provide the reinforcement in the compression zone, we'll see here. So generally tension zone reinforcement will be provided to arrest the tensile cracks. But in doubly reinforced beam, we'll provide the reinforcement in compression zone also. Why we are providing reinforcement in compression zone? Why? Because first reason is to reduce the depth of beam. To reduce the depth of beam. And second situation is to, if the beam is a continuous beam, so some situations where at support negative moment, that is a negative moment will be developed at the support. At the support, the tension will be developed at the top. So tension at the supports in continuous beam, if you take a continuous beam, if you draw the bending moment diagram, so this is the variation of, let us suppose it is simply supported. So this is the variation of bending moment diagram for the loading. At this inner support, the tensile zone will be developed at the top. So right, in this situation, for the continuous beams, we have to use doubly reinforced beam. This is the second situation. First situation where the depth of beam is restricted. When the depth of beam is restricted, we have to go with a doubly reinforced beam. And the third situation is where the stress reversal may possible due to accidental loads. Due to accidental loads, stress reversible may possible. In that situation also, we can use doubly reinforced beam. What is meant by stress reversal? Stress reversal is nothing but So compressive forces, compression will convert to the tension will convert to the compression due to unexpected accidental loads. Because it's accidental load, the bending moment may change positive to negative, negative to positive. In that situation also, we may use doubly reinforced beam. So these are the necessity of doubly reinforced beam. So now we'll see the analysis of doubly reinforced beam. So in working stress method of design for the analysis of doubly reinforced sections or singly reinforced beams, we'll use modular ratio. We'll convert equivalent section, will convert the section into equivalent section. That means so it's a composite construction. So concrete and steel construction, reinforced RCC construction is a composite construction. So we have to convert the strength of steel and concrete is not same per unit weight. Strength of concrete per unit weight and strength of steel per unit weight is not same. So to transform that strength per unit weight, so I want to, so in working stress method of design, we need to convert the strength equal in terms of quantify the scale. So we have to convert the strength into, for the quantification, we have to convert into scale, right? If you see here, equivalent section we need to convert. So, right. So equivalent section of concrete. So this is the concrete portion. So for the to take care of compressive forces, top fibers. So top fibers under compression and bottom fibers are in tension. So in general, simply supported beams. So right, concrete portion will active to take care of compressive forces. Right. So this is the compressive area, but steel compressive strength is more than that of concrete. So steel is provided here. So steel compressive strength is more than that of concrete compression strength. Right. So we have to convert the steel strength into concrete strength. So right, actually steel strength but we are projecting here in this location. So steel strength is more. How much more? It is ASC into MC minus 1 times more than that of concrete. AC into MC minus 1 times of more than that of concrete. So at this location, we are converting equivalent concrete strength. At this location, steel strength is equal to equivalent concrete strength M into AST. Equivalent concrete strength of steel strength, that is equivalent to equivalent section in terms of concrete. So M into AST. Now stresses at the top fiber will be sigma CBC. So stresses at the rebar level, this is this level, in this level, sigma C dash. And the stress at the bottom fiber, sigma ST by equivalent stress, sigma ST by M. Equivalent stress at the bottom fiber, sigma ST by M. Right? So now, first I want to calculate net compression area of this compression zone as well as tension zone. So if you equate net compression zone in concrete and steel, then we will going to get neutral axis depth. So neutral axis depth is N. I am considering neutral axis depth is N. Effective depth is small d. Effective depth is small d. Effective cover. This is d dash, d dash. Okay. So this portion will be N minus d dash, N minus d dash. So this portion will be d minus N, d minus N. Effective depth minus neutral axis depth. Right? The distance between sigma C dash and a sigma ST by M, this is D minus D dash. The distance between sigma C dash and sigma CBC, this is D dash. Right? So now I want to calculate compressive area, equivalent compressive area. Equivalent compressive area is equal to, first one is B minus L. So B minus L. So this is the width of beam is B. Area, I want to calculate equivalent area of this section. So it is B and neutral axis depth is N. So Bn. In this Bn, we need to deduct area of steel. Equivalent area ni calculate చేస్తున్నాం in terms of concrete. Bn. ఇందులో నుంచి స్టీల్ ఏరియా తీసేస్తున్నాను. ASC. యాక్చువల్ కాంక్రీట్ మొత్తం ఉంటుంది, బట్ ఇందులో స్టీల్ ఉంటుంది కాబట్టి కాంక్రీట్ ఏరియా నుంచి స్టీల్ ఏరియా తీసేస్తున్నాను. So now I got area of only area of concrete. Now I am converting steel area in terms of equivalent strength of concrete, equivalent section in terms of concrete. So right, so we need to add it. It was by multiplying modular ratio of transformed section, MC into ASC, MC into ASC. So this is your area of this equivalent compression zone. So compression zone area. So now if you simplify this, BN plus I'm taking common ASC MC minus 1. So this is your area, net compression area, This is your net compression area. So that is we are written here, right? So now if you see net steel area, this is a net compressive area and a net area, right? Net area for the equivalent concrete at tension zone will be equal to MC into ASC, right? So now we'll see. So now I want to identify the neutral axis depth in terms of stress, in terms of stresses in the fibers, right? So we'll see here. So let us say this is the variation of a stress variation diagram. So this is sigma st by m, equivalent stress at this level. This is sigma cbc. So if you take this rectangular section, this is neutral axis, let us say. At the neutral axis, stress is 0. At the top fiber, sigma cbc. At the bottom fiber, sigma st by m. So this is the neutral axis depth n, and it will be equal to d minus n. So now from the similar triangle, if you write sigma cbc by n is equal to sigma st by m divided by, from the similar triangles I am writing here, d minus n. See, we can write like this. So sigma cbc by sigma st is equal to n by d minus n. So this is your the stress diagram. From this, if you know the stress in concrete, you can able to calculate stress in steel. You can able to calculate stress in steel, right? So from this, you can calculate stresses. From the neutral axis depth concept, you can calculate. If you know the stress in concrete, you can able to calculate stress in steel at the different levels, of loading, right? Now I want to calculate neutral axis depth for doubly reinforced section. Neutral axis depth for the if you want to calculate neutral axis depth for doubly reinforced section, we have to equate moment of compression area about neutral axis should be equal to moment of tensile area about neutral axis. So now just now we are calculated the uh, compressive area, right? This is the compressive area V into N. So now I want to calculate about this neutral axis. I want to calculate moment about this compressive area. So how are we going to get the moment? The area moment is equal to area into perpendicular distance. Area into perpendicular distance. So total area will be concentrated at a distance of n by 2 from the neutral axis. N by 2 neutral from the neutral axis. I'll going to write here moment is equal to Bn into n by 2 minus Bn into n by 2. The steel area is located here. So CG of the steel area will be here. So moment is equal to area moment is equal to area into perpendicular distance ASC. So we need to deduct the steel from this concrete portion, ASC into d minus d dash. So that is not d minus d, n minus d dash. It is n minus d dash. So this is a neutral axis depth. Neutral axis depth నుంచి తీసేస్తానికి ఈ portion వస్తుంది. n minus d dash plus equivalent steel area, equivalent concrete area in terms of steel, equivalent concrete area in terms of equivalent steel area in terms of concrete, right? That is area is ASC. So equivalent concrete area. So just whatever here we are calculated that written here, and where it is located at a distance of n minus d dash. Again it is located n minus d dash. ఈ లొకేషన్ ఎక్కడ ఉంటుందండి? ఈ లొకేషన్ ఎక్కడ ఉంటుంది? n minus d dash మధ్యలో ఉంటుంది, right? Into n minus d dash. So this is your equivalent moment. So for calculation of neutral axis depth, we have to equate. This is the compressive moment and tensile moment, right? This is the moment of compression area, and we have to calculate moment of tensile area right? Moment of tensile area we have to calculate, and if you equate both, you're going to get the neutral axis depth. Right, now we'll see moment of tensile area will be equal to m into AST. We are taking moment about neutral axis, so this is the moment of tensile area is m into AST. So it is located at a distance of d minus n from the neutral axis. D minus n from the neutral axis. So if we equate these two, you will going to develop neutral axis. You will going to calculate neutral axis depth. That is a moment due to compressive area and moment due to tensile area. If you equate these both, you will going to get neutral axis depth. Right. So this is the how we are going to calculate the neutral axis depth. Right. So generally the relation between m and m dash, the relation between m and m dash will be relation between m and mc is equal to 1.5 times of m. So this you need to remember. So maximum compressive stress in concrete sigma cbc. The equivalent concrete at the level of compression steel will be sigma c dash, and equivalent concrete at the level of steel, equivalent concrete stress in equivalent concrete at the level of tensile steel will be sigma st by m. Just now we have written here. So this is sigma c dash and sigma cbc. Stress in steel is sigma st, right? So this is the, so now moment of resistance will be equal to moment of resistance for the doubly reinforced beam will be equal to moment of resistance of doubly reinforced beam is equal to MR will be equal to moment of resistance due to singly reinforced section plus moment of resistance due to the reinforced compression reinforcement. Moment of resistance due to tensile reinforcement and moment of resistance M2 is a moment of resistance due to additional reinforcement provided in the tension zone to balance compression reinforcement. So this moment of resistance will be equal to, so this is M1 and M2, right? So this will be like that we're going to analyze. So M1 is equal to, so compressive area will be there and the tensile area will be there. So moment of resistance due to compressive force will be one aspect, moment due to tensile area. So tensile load carrying capacity బట్టి మూమెంట్ ఉంటుందండి, కంప్రెసివ్ లోడ్ carrying capacity బట్టి మూమెంట్ ఉంటుంది. So both moments we need to consider. The first only compression, if you take compression, so ultimate moment carrying capacity is equal to M1. This is due to concrete and M2. This is due to compression steel. M2 will be equal to compression steel. So first moment, ultimate moment carrying capacity due to compression and ultimate moment carrying capacity due to tension. So compression ఏమున్నాయి, కాంక్రీట్ ఉంది, కాంక్రీట్ ది M1 అంటున్నాం. M1 ఎట్లా రాస్తున్నాం మనము, హాఫ్ ఇంటూ సిగ్మా సిబిసి ఇంటూ బి ఇంటూ ఎన్ ఇంటూ డి మైనస్ ఎన్ బై 3. సో ఇది ఒక ఈక్వేషన్. Or you can use r into bd square. So we can write, generally we can write half into sigma cbc into b into n బదులు మనం k into d అని రాస్తాము. ఇది j అంటాం. j అంటే దట్ ఈస్ 1 minus k by 3 అంటాం కదా. సో దీన్ని ఏమంటే jd square అని కూడా jd అని రాయొచ్చు. సో ఇఫ్ యూ రైట్ దిస్ half into sigma cbc into k into j into bd square. So this half into sigma cbc into k into j is a constant. This can be written as r into bd square, right? So adokati. So this is compression concrete and steel కి రావాలంటే C2. So it is located here. So d minus d dash moment is equal to idoka moment and this is compressive concrete and it is due to compressive steel. C2 into d minus d dash. What is C2? So C2 is equal to, again we can write C2 is equal to MC minus 1 into AC equivalent area of concrete in terms of steel. Equivalent area of concrete. MC minus 1 into AC into sigma C dash. Okay. That is compressive stress. C2 వస్తుంది. C2 వచ్చిన తర్వాత you can able to calculate M2. Right. So now moment of resistance will be equal to, due to compression, moment of resistance due to compression will be equal to half into sigma cbc b into x into d minus either x అన్నా కూడా n అన్నా కూడా neutral axis depth, b into n into d minus n by 3 plus 1.5. ఇక్కడ mc బదులు 1.5 m అని రాస్తుంది. mc 1.5 m minus 1 into ac sigma c dash d minus d dash. So this is the ultimate moment carrying capacity due to compression. Now you can calculate by using tension also. From the tension also you can able to calculate directly. You can calculate, okay. So this like that we're going to calculate ultimate moment carrying capacity in doubly reinforced beam. Thank you, Ananda.